This is the continuation of the tutorial series on kinematics of mechanisms, video 5 out of 10. So we'll be covering what is a mechanism and how do we derive degree of freedom of a mechanism using Grubler's Kutzbach equation. And also that is applicable for 2D and 3D variation that we'll just briefly discuss upon. Okay, so a mechanism consists of set of rigid bodies. Generally, sometimes they can also use flexible body, but we'll be focusing on rigid bodies, and they have connections connected using something known as joints, and they have prescribed motion. Okay, so this is very broad definition of a mechanism. It is a kind of something known as a machine, or it is a part of a machine. So typically there could be question related to how do you define mechanism, how is it different from a machine, so you can figure it out. Okay, now let's look at the derivation for Kutzbach equation. So imagine I have a rigid body. In one of the earlier tutorials we have covered this part. This particular rigid body, similar to my phone, if it is on a particular plane, it can translate in two direction. It can also rotate about z direction such that it does not come out of the plane. So each rigid body, or let's say this particular rigid body, has two translation and one rotation. So you may please refer to the earlier videos. So rigid body has 3 degrees of freedom. Now, what do we mean by degrees of freedom? That is number of independent motions possible in a system. Okay, so degree of freedom for this is 3. That is 2 translations and 1 rotation. Again, you may refer to the earlier video. Now let us look at a system which has multiple rigid bodies. This is, let's say, body number 1, body number 2, body number 3, so on and so forth till body number n. So n is the number of rigid bodies. Okay, now each body will have 3 degrees of freedom. They are independent. I mean, they are not connected at all. So degree of freedom of this system is going to be, each body will have 3, so we'll have n bodies, so degree of freedom is 3 into n. Fair enough. It's just that they are able to move around. If they are hitting each other, we'll avoid such situation. Let's assume that they don't hit each other or not. Okay, next what do? We try to make one of them fixed, and we'll have n. So n is still number of bodies. N minus 1 will be number of moving bodies. So degree of freedom in this case is, see, the first guy will not be able to move. It's not possible to move, whereas these guys will be able to move. So that means each moving body will have 3. So number of moving bodies is n minus 1. So degree of freedom of the system is 3 into n minus 1. Okay, good. Now let us try to expand beyond. I'm going to start introducing something known as a revolute joint. A revolute joint means, let's say I have a fixed link like this. I have another link or rigid body, and with them I have connected using a revolute joint. This is a revolute joint, or I'll call it as a hinge joint, like door hinge. So whenever we have a door hinge, it only allows one relative rotation. So there is a rotation possible between body number 1 and body number 2. Okay. So how is that rotation seen? So I'll be able to represent this motion. Now, visually, you can understand that degree of freedom of this system is there's only one rotation possible. Motion is possible. Okay. Degree of freedom is 1. Now, how do we get that? We'll do some mathematical derivation shortly. Similarly, if I have another fixed link, there's a joint like this. There's one joint here. There's another joint between this. Body number 1, body number 2, and body number 3. Now you can imagine the motion now. With respect to 1, 2 can have rotation. So this is rotation of 1 with respect to 2. Similarly, there's a relative rotation possible between 2 and 3. So I'll call this as 2 and 3. Okay. So as you can see, there are two independent motions. I can only rotate one, only rotate second, or a combination of both. So that is degree of freedom of this system is it has two independent motion. Okay. Similarly, you keep on extending it, and then what you understood in this is, let me try to use a different color. This scenario. Earlier, I had one body. I had another body. Okay. Now this body, if I don't put any joint, it had translation. I could translate, assuming that again there's no, they are in different planes. Okay. And I can also translate like this, and I could also rotate it. Okay. I could rotate this. So it had 3 degrees of freedom. The moment I introduced a revolute joint here, what happened? If this is fixed, I can't move it in this direction. So this guy is gone. Okay. I cannot also move in this vertical direction because then it will break the joint. So this motion is also not possible. However, I can do this relative rotation. So this is possible. So can we deduce something here? So what it means is I can write degree of freedom as, let's say, 3 into number of moving bodies, okay, minus every joint I introduce. Every joint, revolute joint I introduce, I am taking away 2 degrees of freedom. That means I can say 2 into, I'm restricted. I'm having a restriction that I can't move this rotation. So 2 into number of rotational or revolute joints. I'm just coming to a generic equation, but before that, whatever we have understood, we should be able to do it. So what will be this case degree of freedom? This will be 3 into 2 minus 1 minus 2, because 2 is the number of degrees of freedom we are losing out per joint. So how many revolute joints you have? One joint. What will this be? 3 into 1 minus 2 into 1, which is 1. Same as what we derived here. Similarly, in this particular case, we'll have degree of freedom is equal to 3 into n is 3, n minus 1 is 2. So 3 minus 1 minus 2 into number of revolute joints. There is one revolute joint here. There's another revolute joint here. 2 into 2. So 3 into 2 is 6. 6 minus 4 is, again, degree of freedom for this is. So we can generalize this in the form of a equation. We'll call that as Grublers Kutzbach BAK equation. What it says is degree of freedom of a mechanism. When we say a mechanism, it will have at least, or it will have one grounded link. Okay. So that is why the term n minus 1 is coming. So for all practical purposes, we'll assume that there is at least one grounded link with respect to which the mechanism is moving. So it is given as 3 into n minus 1 minus 2 into number of joints which have one relative degree of freedom. Okay. Similarly, we can also extend it further by saying this J2. So different textbooks have different way of writing P1, J1, K1 like that. So in this particular manner, I'll write n is equal to number of bodies. N minus 1 is number of moving bodies. Okay, now J1 is number of joints with one relative degree of freedom. In few textbooks, it is also mentioned as something known as lower pairs. So lower pairs have surface contact. Okay. In one of the earlier videos, I have very briefly discussed about lower pair. So they have surface contact. So typical examples of one relative degrees of freedom are revolute joint, prismatic joint, if you are dealing with 2D scenario. Okay. Now, what is J2? J2 is number of joints or pairs, kinematic pairs with two relative degree of freedom. Okay. So again, in few textbooks, it is also written as higher pairs. The higher pairs have line or point contact. Okay. So typically, whenever we deal with gears or cam followers, so in gears, basically when the gears mesh, there is a point contact if you're looking in 2D space. Okay, the point is moving where the contact is happening. Similarly, if there is a cam, when the cam is moving, the follower goes up and down. So there is also a point contact. So we have to count those types of pairs and accordingly count it as J2. Okay. So this is Grubler's equation for 2D mechanisms or planar mechanisms. They move in a plane. Now what will happen in case of a 3D mechanism is, very briefly I'll explain, is this. If you have spatial mechanisms, in 3D. So if I have a rigid body, so it has 6 degrees of freedom. A free rigid body will have 3 rotations and 3 translations. So if I have n, so there will be 6 into n. If I fix one of them, then it will become 6 into n minus 1, where again n is number of bodies, n minus is number of moving bodies. Now, similar to what we have here, it's very easy to understand with when we look at this. So this number is how many we have restricted. This number is how many we allow. So total should always be 3 in case of 2D. Similarly, in case of J2, each joint has 2 relative degrees of freedom. Therefore, it has one restriction. So 2 plus 1 is again 3. So when we extrapolate that, so if I have J1, number of joints which allow one relative degree of freedom, so that means it will have 5 restrictions. Okay. So we are reducing those many degrees of freedom. That is what it means. So 5 plus 1 will become 6. Similarly, if I have J2, 2 are allowed, 4 are restricted. So those many degrees of freedom are getting reduced. Similarly, J3 will have 3. Similarly, J4 number of pairs which restrict or which have 4 relative degrees of freedom, it will have 2 restrictions minus J5. If at all we have any pair which has 5 relative degrees of freedom, it will have 1 restriction. So this is a way to find degree of freedom of a spatial mechanism, and it's a generic uh, equation for degree of freedom of a spatial mechanism. So in the next video, we'll be considering few standard examples of mechanisms, and we'll try to find out the degree of freedom. So please remember, 6 is a number for 3D, 3 is a number for 2D, because that is the number of degrees of freedom allowed for a free body in that scenario. And these two, when you add 5 and 1, 4 and 2, it should add up to 6. So it's how many degrees of freedom we actually reduce. And this is in line to the another definition we had studied earlier: total number of parameters minus number of constraint equations. Constraint or constraints. Okay. So these are basically constraints. How many constraints there are, how many freedom is there, how much constraints are there. So that is what is the overall picture. Sometimes it is also given like this: x into n minus 1 minus summation sign something something will come. So whenever summation sign comes, people may get confused. So this is easier to remember: 5 plus 1, 4 plus 2, 3 plus 3, like that. So in the next video, we'll solve few problems. Thank you.